Okay. Good afternoon, everyone. It's right. We'll start the class. So, last time that we met, right, last week, we had a discussion about states of matter last. Can you remember? Right. I wanted to talk about mainly state properties or state functions. Now, usual analogy that is taken when it comes to state functions is a very simple one. What you do is, now you think of a place like Adams Peak, right? Let's say when you go to Adams Peak, have you ever been to Adams Peak? Right. So if you think of Adams Peak from what do you call it, sea level, let's say this peak is at, anyone knows the exact value, how tall the Adams Peak is? Siripad? No? 1,800 meters. Right, let's say, just round it off, let's say 2,000 meters. Right, 2,000 meters, that means 2 kilometers, right? So this is the sea level, right? How much? 2,000? 2,200. We'll round it off to say 2,000, right? Now, imagine if you, let's say you are carrying a backpack and going there. Your backpack weighs about, let's say, 2 kilos, right? So, if you have your backpack here at sea level, this is your backpack. If you have the backpack at sea level, what is the potential energy there? Zero, right? Because sea level means the elevation is zero. Potential energy is calculated how? Yes, potential energy is equal to mgh, mass into gravitational pull into height in meters. Sorry?
Is that a wedged marker?
Yeah, it's a wedged mark. Earlier also, this is a bit new, that's why. Right? Anyway, so when it comes to these, if you have gone to Adams Peak, you know there is this one path that you can take that is only having stairs in it, right? It's actually, if you have used it, you know it's a bit difficult to climb. Have you gone in the other direction where you have like it's a bit of a scenic route, Kuruvita Trail? Yeah. So there, to a certain extent, you go through the forest and then you have the stairs.
How to randomly climbing those stairs?
Yes. So now students, now imagine this is the staircase route, this is the Kuruvita Trail, and then you have, imagine someone has built a lift there, right? From bottom to the top, a lift, right? Yeah, Elon Musk came and made a lift. Now imagine, regardless of what path you take, imagine you took the Kuruvita Trail or this. Now if you, let's say if you go in this, you are putting in a lot of effort to climb. Does that mean your backpack over here will have more potential energy? No. What about this route? What about this route? So depending on the route, does it change the potential energy that it has? No. It only takes into effect the elevation. And the rest of the factors are the same, no? Mass of the backpack and the gravitational pull is the same. So the path is not a matter for concern. As long as the elevation is the same, backpack will have the same amount of potential energy regardless of what path you took. So just like that, students, when it comes to state functions, regardless of where or regardless of how you got to that particular state, the amount of energy in that substance at a specific state is the same. Now, for example, if you take water, right? I will erase the, you understood this analogy, right? So if you take water, maybe I'll erase this bit. If you take water, let's say you have water at room temperature, right? Let's say 1 liter of water at 25 degrees Celsius. Now this 1 liter of water will have a certain amount of energy. You know, based on the temperature of a substance, the substance has certain amount of energy in it. Now we'll take the same number of water molecules here. Let's say we have it in solid form. Let's say the same number. Imagine this has x moles of water. We have the same x moles of water here, right? But now this is at, let's say, minus 2 degrees Celsius, right? You take it out and you leave it outside until it reaches this temperature, right? So now it comes to the room temperature 25 degrees Celsius. So it has now come to this point. Now let's take another example. Imagine you have a bit of steam, right? You have turned exactly X amount of moles of water into steam. Now imagine this is at 102 degrees Celsius, right? And you allow it to cool to room temperature 25 degrees Celsius. Now regardless of how you got to this point, whether it was from a higher temperature point or a lower temperature point, as long as you come to the same condition, which is 25 degrees Celsius and X amount of moles, what can you say about the energy that they obtain at this condition? Same. Is that clear? So when it comes to a given substance, if you have outlined the conditions that it is in, so usually as conditions we mainly look at the pressure and the temperature, right? Usual pressure in normal laboratory environment is how much? 1 atm. Temperature is how much? 25 degrees Celsius. Usually we take 298 Kelvin as the room temperature, but keep in mind we will talk about standard temperatures and all that in a second, but for the time being, usually in our observations, whenever we are talking about anything, you have to always use 1 atm pressure whenever we are talking about enthalpy or energy. Temperature might vary. Temperature is not fixed because certain processes happen at a higher temperature.
1 atm is because it's coming the same.
Yes, usually we can have hyperbaric chambers where pressure is elevated or vacuum chambers where pressure is decreased. But a majority of the reactions that we do them at room temperature pressure conditions. Mainly the room pressure, right? Usual pressure, right? Students, can you please bear with me for just 2 minutes? Okay, so as I was saying, the pressure is always 1 atm, and then when it comes to temperature, it might vary because certain chemical processes normally have different temperature values. Right, we'll move on out of that for the time being. And if you take a look at the next part, now I told you when it comes to our enthalpy changes or energy changes. When you are talking about a chemical reaction, it's enthalpy or energy change. You have not heard the word enthalpy yet. So let me tell you what enthalpy is. Enthalpy is basically a chemical reaction's energy change that is measured at a constant pressure process. Meaning, if you just do a small chemical reaction, we'll take a simplest one, hydrogen gas reacted with oxygen gas, and we produce H2O liquid, right? Gas. Okay, so now over here, if you carry this process out at 1 atm pressure without any changes in the pressure, because actually when it comes to atmospheric pressure there is not a lot of variations, unless and otherwise you do it in a pressure chamber and pressurize the system and do it, that's a different story. But if you just do it open in the air, basically if you collect hydrogen gas into a test tube and just bring a lid splint, what happens? Hydrogen gas comes into contact with oxygen, burns. This is happening in a open system, and the pressure is maintained at 1 atm. Clear? So at that point, students, you don't necessarily have a pressure change. So the energy change that takes place, you will see energy is released. The energy change that is taken place here can be considered a enthalpy change. We are using the word enthalpy. So enthalpy is the energy of substances that is measured at constant pressure. Energy of this substance measured at constant pressure. Energy of this substance measured at constant pressure. Same goes to these two as well. Do you understand? But determining an individual substance's energy, imagine if you take this, the energy of this at constant pressure you can't properly measure accurately. However, if I convert this into something else, imagine you burn it, you turn it into ash, right? So when you convert this from here to here, you have a shear problem, right? If you convert it from here to here, then what happens is, at that point, students, let's say you take this and then turn it into ash. So at that point there's going to be energy release or energy absorption. That can accurately be measured. There are methods, we'll be learning about them today. And that energy change measured at constant pressure can be referred to as a enthalpy change. Is that understood? Right. Anyway, I have the note here. Hopefully you would have gone through it by now. So refer to that and see. And then we have standard state. Take a look at what a standard state is. Now standard state, bear with me a second, right? When it comes to writing a proper state for, let's say I told you, when you're depending on where you go and how you go, the distance between two places will not change, right? Here, if I write the same equation, 2H2O gas plus O2 gas and turns into 2H2O gas, if you write it like this, do you feel like we are talking about the same destination or same reaction? No, right? Actually, this is a further away destination, I would say like that. Why? At room temperature pressure conditions, what is the most common form of water? Liquid, right? Then, if you take water liquid in liquid state, if you want to turn it into a gas, what do you have to do? You have to provide more energy to turn it into a gas, right? So over here, the energy difference between what happens over here, so when these reactants go to this location, the energy difference is going to be slightly more different to the energy difference here. I will give you with examples later. Here, majority of the energy is released, right? We are going to this location only. However, when it comes to this process, the same amount of energy is released, but some amount of energy is reabsorbed to do what? Turn liquid water into gaseous water. Do you understand? So what is the net release of energy? Only this much.
Enthalpy is less than.
Sorry?
Enthalpy is less.
So therefore here the enthalpy would be smaller, like it's an exothermic reaction, so enthalpy value, I will talk about the negative positive signs, but here the magnitude of the enthalpy is smaller. Is that understood? You release the same amount of energy to turn it into H2O liquid, but H2O liquid might turn into H2O gas depending on the conditions. So for it to turn into a gas, it should absorb energy. Is that clear now? And therefore there is an overall energy release, but that energy release is smaller than over here. Is that clear? So mentioning the states is very, very important, right? So turn to page number, turn to page number 8, standard state. Please read through that part. If you are done reading, let me know, so I can give you a small note on it. Right, so do you understand what it says? Now, write a new heading, standard state. I will give you a bit of a simplified version of it. Standard state. Standard state is the state of a material. Standard state is the state of a material at a defined set of conditions. Standard state is a state of a material at a defined set of conditions. Standard state is a state of a material at a defined set of conditions. At defined set of conditions. Those conditions are semicolon, right? Those conditions are, and put a semicolon. First we talk about pressure, right? Pressure equals 1 atm. pressure equals 1 atm. So usually students, we can write 1 atm as 1.013 into 10 to the power 5 pascals. Sometimes you can see in certain questions it is rounded off to just 10 to the power 5 pascals, right? Without having to write 1.13. Sometimes they just write 10 to the power 5. So follow the instructions of the question based on the question, right? And then you can write temperature, right? Temperature is undefined. Temperature, what we call as a standard temperature, is undefined, meaning depending on the state we are looking at, the temperature might vary. But within brackets, please write, you can write generally (25°C) is taken as the temperature, of the standard state. It's a generalization though, but keep in mind for different substances their standard state is going to have different conditions. I will elaborate on this bit more better after this note. Yeah, when it comes to iron and all that, there is an example, right? I will talk about that, right? So, and then let's say concentration. Certain substances have a concentration, right? So then we have to define the concentration under standard state. So that is a defined value. You can write concentration. Concentration is 1.0 moles per decimeters cube. 1.0 moles per decimeters cube. Now I will explain this to you through a small example, right? So that will be the easiest thing to do, right? Now, if you take formation of water, there's something called, students, in the near future you will be learning. If you are carrying out a chemical reaction under standard, or if you are carrying out a chemical reaction under the constant pressure, energy change that is referred to, that is taking place is referred to as enthalpy change. So there are so many different types of enthalpy values that are tabulated and you have to learn about. Now one such very easy enthalpy change is enthalpy change of formation. Formation enthalpy, meaning when you are producing water starting from its constituent elements. Now water contains what elements? Hydrogen and oxygen. So when you have water formed starting from hydrogen and oxygen, what is the energy change that takes place, right? So let's say we call it formation enthalpy of water, and in that formation enthalpy there is a definition. In that definition they say we are only looking at when you are producing 1 mole of water, how much energy is exchanged, right? So we write the equation like this. We want to produce just 1 mole of H2O, right? And then we try to balance this. So we have O2, basically half a mole of O2 should be taken, and hydrogen you have to take 1 mole. Then only you get only 1 mole of water here. Is that clear? So now when this chemical reaction is taking place, there will be a certain amount of energy lost. So this amount of energy, if you have produced exactly 1 mole of water here, that amount of energy that is released is referred to as the enthalpy change of formation of water. Is that clear? So now when you are defining very precisely a formation enthalpy or different enthalpy values, it is very important to have the right state Because if you use a wrong state, like I explained earlier, if you use the wrong state here, like gaseous state, this energy value is going to be different. Now for example, if I say go to Colombo and come back, then you could ask me, go to like which part of Colombo, where, right? It's very arbitrary, like it's not defined properly. But if I say, okay, go to Colombo, Liberty Plaza, this particular shop and come back, right? Then you know exactly how long it will take. You can put Google Maps, you know the distance, and for you to go back and come back, you know exactly how long it will take, maybe how much it will cost you also, you would be able to calculate. Is that clear? But if I just say hydrogen reacts with oxygen to form water without defining the states, then the amount of energy that is involved here is unknown to us. Now for example, when we say hydrogen gas and oxygen gas as well, they can also be in different states. Hydrogen gas at 25 degrees Celsius temperature versus hydrogen gas at 100 degrees Celsius temperature will have different energies. Is that clear? So we have to have what is known as a standard state. We bring in a definition saying we have something called standard state. Meaning what? For each substance or each element or each substance, we have what is known as a standard state. It is outlined. Meaning, now if I say, tell me the standard state of gaseous hydrogen. Gaseous hydrogen standard state is when the pressure is 1 atm and temperature is 25 degrees Celsius. The gaseous hydrogen we have is referred to as standard state hydrogen gas, right? But imagine 1 atm pressure and let's say 200 Kelvin or 200 degrees Celsius temperature. Is that at standard state? No, right? So usually standard state of an element is defined by its conditions, pressure and temperature conditions, and so when it comes to certain things, concentration also should be taken in. Is that clear? So what is the standard state of water? At room temperature pressure, it's liquid. So liquid water standard state is 25 degrees Celsius temperature and 1 atm pressure. But for certain elements, we have very specific standard states. They say when it comes to iron, they say for solid iron, or else in other words for Fe solid, they say the standard state is pure iron at 1 atm pressure, and what is the temperature? 500 Kelvin temperature. Is that clear? Do you see? That is defined. That's in data booklets. It's basically defined, outlined, and said, okay, if you are referring to ferrous solid, basically its standard state is pure iron. This is referred to as the standard state, or we can say standard state. And what is this? What are these? These are our standard state conditions. Standard state related conditions, not standard conditions, standard state conditions, right? So do you understand now? So when it comes to liquid water, it will be H2O liquid at 1 atm pressure and 298 we can say 25 degrees Celsius or 298.15 if you are being very specific Kelvin temperature. So again, this is the standard state of water, most abundant form of that particular substance in those given conditions. So these conditions, what is the most abundant form of water? H2O liquid. So standard state conditions define the standard state. Is that clear? So different substances, basically there are different standard states, but it's very easy to figure out, you just think of, for example, if you say sodium, what is the standard state of sodium? Solid. What could it be? Could be the conditions, most probably, but we have to double check. 1 atm pressure, the double checking part applies to the temperature. Temperature could be slightly different. Now, solid iron is present at room temperature, no? But we can see according to the actual standard conditions, 500 Kelvin, right? So that is the outlined value they have given. Is that clear? So we can't just randomly go on saying always 25, 25, 25. Some could have a different value. That's why in the textbook itself, it says temperature is undefined. It generally, unless and otherwise stated, we generally take it as 25 degrees Celsius. But for certain substances, the standard state temperature condition might vary. Is that clear? Understood? Right? So why do we do this? So that we know where we are starting and where we are going. Right? We know exactly when you write H2 gas, meaning we are talking about hydrogen gas in these conditions. So we have an idea about its energy at that point. And oxygen gas in these conditions. Otherwise, when you say oxygen gas could exist in even 200 degrees Celsius temperature. Right? So what temperature? We have to specify. So when you write an equation like this, it's very clear if this is in the standard states, what we are referring to. Is it understood? Otherwise, this energy value could vary from, like, one person to one person. Imagine you do a reaction in 25 degrees Celsius conditions and one person does in Sri Lankan temperature. What is the Sri Lankan temperature value? Right? 37 degrees Celsius or maybe like that much, right? So then imagine at that point this energy value differs. Is that clear? Now, similar situation is when it comes to biology. Right? Sri Lanka, we have jackfruit. We say cos. Normally we refer to it as cos, no? So we have cos. They have jackfruit. Maybe in another country another name. But what is the name for cos here in scientific notation? So scientific naming. And none of you are biology students. Artocarpus integra, right? If I'm not mistaken. So I haven't gone to that part. I'm sorry. Right. So, but it was in O levels, this name. Right. So, anyway, when it comes to, see, do you understand? Then, no matter where you encounter the same species of that particular jackfruit, okay, the name is the same. Right. Whether you are Sri Lankan or Australian or whoever it is. Just like that, when it comes to writing an equation, if these states are properly outlined and their conditions are properly stated, no matter where in the world you do it, while adhering to those conditions, the energy change you get should be the same. Is that understood? Right. So, yes, please take this down, students, as an example. Take this down as an example. For liquid water, the standard state is this. And please write this as a standard state condition, okay? You get the idea, right? It's difficult for me to bend and write. So right here, this is the standard state conditions for H2O liquid. Done? Okay? Sometimes a lot of the students have a misconception, actually some teachers also, a misconception about this? If you had any, hope now it is cleared. Is it clear now?
Usually what kind of misconceptions?
They think standard state is just 1 ATM 25, and then there's usual, like,
It's
yeah.
25.
But it could change. And then when you write standard state condition, some students think it is, can you remember STP conditions? I will talk about that after this. I'll talk about that after this, because that is also important. So standard state conditions are different to STP, okay? Let me know when you're done taking this down. Are you done? Done? Okay. Okay. Right. Until you all copy it down, I will talk to you about what STP conditions are. Can you remember we learned when we were learning Unit 4, there was some condition called STP, standard temperature and pressure conditions, and standard ambient temperature and pressure conditions. Can you remember those? Right. So that is different to standard state conditions. Okay. Standard state condition basically means for each element there are what is states considered as standard state. That means the physical state, right? Standard states, and the conditions that define this state is referred to as the standard state conditions, right? Often sometimes mixed up with standard conditions, but we actually generally call them standard conditions as well, right? Anyway, that means the standard state of pure iron is defined by these temperatures. If this slightly pressure and temperature actually, if this temperature slightly change, we don't say iron is in the standard state at that point. Is that clear? Right. Anyway, so when it comes to standard temperature and pressure conditions, STP, that is a different story. STP is a defined temperature pressure value. STP. What are the STP conditions? Standard temperature pressure. What is standard temperature? 0 degrees Celsius, right? 0 degrees Celsius. And pressure? 1 atm, right? So if you are being very specific, this means 101, 325 Pascal. And what about this? Be very specific. Tell me what this is. This temperature is 273.15 Kelvin. Correct. If you are being extremely specific, that is the correct answer, right? So what about standard ambient? Usually referred to as SATP, right? Standard ambient temperature and pressure conditions. That one is 25 degrees Celsius or 298.15 Kelvin. Pressure is the same, 1 atm or 101,325 Pascals. Is that understood now? Right? So these are outlined and these are well known. That doesn't mean you can say always now and plus. When you sometimes once students write our standard temperature pressure, they think these are the ones. No. Always, so whenever when you talk about when you talk about standard states of different elements, this is not always the condition. Maybe for a certain amount of the time. They say no, whenever temperature is not defined, take it as 25. So yeah, we can say more often than not this is okay to be used, right? But that doesn't mean. Now, but the problem is if student starts thinking all of the chemical substances have only these conditions, then we can't explain certain things like standard state of iron. Right? There are certain substances where their standard state is happening at a higher temperature. Then what? How do you define that without using different temperature value? Right? So then you will not be able to understand this part very well because you are stuck in this mindset. Okay? So come out of that and understand standard state means for each different substance there are different standard state conditions that are given. Right? You don't learn about all of these separately. Imagine you don't learn iron standard conditions are these. For like an aluminium standard conditions are these. You don't learn separately, right? But you have to have the understanding that there are separate standard state conditions. Is that understood? But when it comes to STP means it is always this. When it comes to SATP mean it is always these values. Is that clear? But for element to element there are standard state related conditions. The temperature value could change. Pressure value is always the same. Concentration value is always the same. Temperature value could slightly change. Right? Understood, Harsh? Yeah. Now, when it comes to this part, now we are done. We will move on to the next part. I want you to take a small note down. Turn to next page actually. Spontaneous reactions and non-spontaneous reactions. These are super simple stuff. Hopefully you already know by now. Tell me an example about tell me a spontaneous reaction that takes place. What are spontaneous reactions? Sorry? Happens? Happens randomly. Okay. Sorry? Doesn't depend on the right. Okay, so you are taking the spontaneous part like the actual meaning of no actual. Let's say you say we want to do some spontaneous activity, like you all of a sudden want to go. No, that's not what spontaneous reactions mean. Here the word spontaneous means happening without interactions or intervention from an external force. Now, for example, there are certain chemical reactions that happen without any external intervention. Now, imagine if you expose sodium to water, after mixing them, do we have to intervene to make them react? No. If sodium comes into contact with water, reaction automatically happens, and it is a very vigorous reaction also. Now, conversely, think about like your gas cookers at home, right? Sometimes you try to turn it on and then the ignition doesn't come, so gas comes out, right? So after a while you forget and you turn it again. Then what happens? A bit of a big, not an explosion, I would say combustion takes place, right? So this is a good example for non-spontaneous reactions. Why? Because earlier also the butane and the propane gas got mixed with air or oxygen. Just because they got mixed, does the reaction take place? No. The reaction would not take place just because they mix. We have to intervene. What is the intervention? Ignition. You have to bring in or provide a little bit of heat or maybe a spark for the reaction to start. Right? So those are non-spontaneous reactions. Spontaneous reactions usually happen on their own. Is that clear? Without an intervention from an external force. So write down a small thing on this small. Right. First one, spontaneous processes. Spontaneous processes. These processes occur on their own accord. These processes occur on their own accord. The transformation of the system from the initial state to the final state is favorable only in one direction. Now, if I'm shedding a bit of light on that particular statement, what that means is you have an initial system, or let's say reactants, and then it turns into products. So when reactants turn into products, it is happening in one direction. So spontaneous processes usually take place only in one direction. If you start with products and try to convert it into reactants, that won't happen. Right? Do you understand? Only in this direction it will be spontaneously happening. If you want to go in the other direction, you have to you have to work. You have to put in a bit of work to do that. Is that clear?
So what about reactions in equilibrium?
So that's a different story. We'll come to that. Right? When it comes to reactions in equilibrium, we learn about equilibrium later on. Since we are not there yet, equilibrium is a lesson that we have to gradually get to. In equilibrium process, what do you know about equilibrium processes? There are certain chemical reaction, students, that happens both in the forward and the reverse direction. So we learn about like equilibrium reactions in the reversible part there. But when it comes to that, the more details about it, about what is referred to as an equilibrium point, equilibrium position, we will cover those later, because I don't want to jump it's a bit ahead and then talk about what happens there, right? But I will give you the definition of what a reversible reaction is. A reversible reaction basically could be considered equilibrium reaction as well, where the reactants can be turned into products as well as products into reactants. You do something like that. Tell me something that you do at home that is reversible. You do it every day. You benefit from it a lot also. Reversible thing. I'll say this. It's a chemical reaction that you do, not within your bodies or anything. It's an external thing that you find it very difficult to live without. What is it? What do you find difficult to live without? External product. Your phones, right? You charge your phones every day, right? So there is a chemical reaction that is taking place. An electrochemical cell is there. So it automatically reacts and turns into products. As it turns into products, electricity is produced, or electrons are given off to run through a circuit, so you have your phone working because of that. And then what do? You plug it into the grid. When the phone is battery is dying, you plug it and you charge it. What do? You provide energy. You are doing some work on it, and then you provide electrons back to the battery and making the reaction that took place to produce the electrons go in the reverse direction. Do you understand? Earlier one reaction took place, electrons were produced. Now electrons are given, reaction is reversed. Do you understand? Right? So this is an example of a reversible reaction. Is that clear? Right? So anyway, that is something to keep in mind. So under spontaneous reaction still, please write down. Many spontaneous processes are natural processes and are irreversible. That means what? You can't change it, like aging, right? Aging is, can you reverse it? No.
But you can add more.
Sorry?
You can add more to it.
Add more to it? You mean like, yeah, you can eat healthy and maybe slow it down a bit. Right? Okay now? Shall we write down the next definition, please? Non-spontaneous processes. These processes do not occur on their own accord. They do not occur on their own accord without any intervention. They do not occur on their own accord without any intervention. You can write example, you can write mixing of LP gas with air. Will not combust. Until a spark is provided. Is that clear? Next one, non-spontaneous processes. Non-spontaneous processes. So not non-spontaneous. The next one is reversible processes. Reversible processes where the system could transform, from its initial state to a final state, and from the final state to the initial state. Right? So those are reversible processes. Now I will tell you a reversible process that are apart from the electrochemistry part of, like, I think the electrochemistry part for some, when it comes to the phone battery thing, might be too advanced for some to remember or understand, but this would be easier. Now have you seen a fizzy drink bottle, right, like this? Usually, does the fizzy drink bottle have any gas bubbles in it? Even when you shake it, do you see it's filled with gas bubbles about to burst? Do you see it like that or no? Until it is open, it doesn't look like it is filled with bubbles, right? A tiny amount of bubbles will appear here because you shook it. But until this tap is open, you see it's clear. That's why you prank other people, right? Like sometimes you shake it and you keep it, right? The person who opens it has a bit of a embarrassing situation. Anyway, what happens is, here what we have done is, when it comes to preparing a fizzy drink, we dissolve carbon dioxide gas in water. This is mainly water, and then other substances are there. We'll forget about the additives like colorings and other things. We'll just think about the water and the carbon dioxide that is present here, right? So what have we done? We have actually taken water. We have actually taken water and reacted it with carbon dioxide. Now, there is an equilibrium or reversible reaction producing carbonic acid. Now, students, carbonic acid is an unstable acid. At room temperature and pressure conditions, it is unstable. It will quickly break down to carbon dioxide and water again. Now, if you imagine somehow produce this, but if you expose it to room temperature pressure conditions, it quickly breaks down to form water and carbon dioxide. Is that clear? So, we have this in here. How do we have that in here? We have actually in this compartment. Now, whenever you are forming the fizzy drink, anyway, we dissolve carbon dioxide in water under high pressure, and it is filled into these bottles at a high pressure as well, meaning in this area there is a bit of carbon dioxide that is at a bit of a higher pressure, right? Elevated pressure. Now, when you open this, what happens? You hear the seal. Yeah, you hear that sound. Why? What is happening here? Pressure is released. Now again, room temperature, pressure conditions. Then what happens? This quickly turns into carbon dioxide and water again. Right? Do you see, as soon as you open it only, it will start to produce bubbles. Until then, no bubbles. Right? Have you seen that? As soon as you open it, you can see bubbles start to come from the bottle. So, why? Because it was reversible. In certain conditions, the forward reaction was possible. In certain conditions, the reverse reaction is feasible. Is that clear? So, this is a good example of a reversible process. Is that clear? Right. So, under reversible process, please also write complete reversibility of a process. Complete reversibility of a process can be done when the changes are carried out slowly in smaller steps. Slowly in smaller steps. Right. So, can you remember this situation quickly? Pay attention. So, what that last sentence means is, now this is the electrochemical cell. Now, this is a good example of what that particular sentence meant. You know, when zinc is connected to copper electrodes, what happens? Electrons could go from zinc to copper. So, slowly what happens? Zinc will dissolve, right? Like this. Right, it will turn into a smaller piece of zinc. You can do this at home actually, it's not that difficult. Actually you can make an electrochemical cell with the use of some household stuff. We'll talk about it when it comes to that lesson. And here this medium is a copper 2 plus aqueous medium. Here electrons are received here. You learned this in O-level, so I can talk about this. Then what happens? Copper gets deposited on this. Right? Now if you want to reverse this, you can do that. what you do is, instead of just having a direct line connecting these two, we can have a power supply, right? We can place a power supply, and the electrons are now going towards this side. Earlier it went from here to here. Now electrons are pulled from this side and given to zinc. Then what happens? Zinc 2 plus ions will get electrons and start to get deposited here, right? So you see it gets formed again, and this layer will get removed. Okay, you see it was reversible, but this reversibility is only there if you do this very slowly, right? Nicely stirring, and if you provide a very uniform small current, this can nicely be not perfectly reversed, like you won't get a nice perfect shiny cylindrical bar, but it will be more or less, most of the atoms will go back in here and will become reversible, right? But if you send a large current all of a sudden really fast, then what happens? The deposition will not be even, right? Some parts could fall off, the addition will not happen properly, right? So some chunks will be here, and here also it might cause some of the amount of the metal to get removed from here, or could cause the thinning of the metal from one end and the rest would fall. Is that understood? Right? So if this section falls off to this point, right, imagine section fell off, is it now completely reversible? Can we create a bridge from here to here? No, right? So something like this happens when it comes to fast charging your phones that are not meant for fast charging. Now there are some batteries that I can't remember the name, anyway, I can't remember the names of these new advanced batteries. Those are designed for fast charging. Imagine, but you have a fast charger and you use it with your very old iPhone or very old Samsung phone, whatever it is. Then what happens? It is not designed for that, right? You are providing a huge amount of current that is designed to take only about 5 amperes. You are sending now 100 watts. So there are 100 watt charges and you have different charges, right? So basically then what happens? The reaction happens really, really fast. After small a duration of using that charger, the battery will swell up and you have to replace the battery, right? So I have seen this happening for some people because they want the newest charger sometimes if they can't change their phone, because at least the phone now battery is dying fast, they want a better charger. The better charger is actually damaging the phone, right? So then anyway you have to buy a new phone after a while. So, marketing, yes. So do you understand now what is happening, right? So when it comes to reversibility, it is better to do it step by step in a smaller pace. Right, and then the last one is irreversible processes. Processes that cannot be reversed. You can write processes that cannot be reversed, or processes that cannot be retracted. Processes that cannot be retracted or reversed are referred to as irreversible processes. Retracted. Retracted means you can't take it back. Many spontaneous processes are irreversible. Many spontaneous processes are irreversible. Example, aging.
Aging of
Sorry?
aging of elements or
Humans, right? Can you reverse human aging? Actually, when you look into it, one of the things that happens is, now those of you who are doing biology, how many of you are doing biology? Everyone? Alright. So basically, every time your cells get regenerated, apparently there is a section called telomeres, if I'm not mistaken. They get shortened. And after that, you can ask this from a biology. I'm not very well versed in this, but this is something that I heard. Then at one point, it will be too thin for it to easily divide, for cells to easily divide. At that point you will start showing signs of aging.
It's like something happened.
It is,
It's technically limiting our motion.
it's technically limiting your own.
So technically, it's
Yeah, so basically at one point you will not be able to divide your cells and it will limit your age, and then you will come to an end naturally at one point. Yes, dust. Right, so now with this we move on to the most important part. Again, students, we move on to the topic called enthalpy, but keep in mind we are touching base on enthalpy and then we move on to energy afterwards, right? And then we come back to enthalpy and learn about the definitions of enthalpy. Now if you talk about a chemical reaction where reactants turn into products, right, where reactants turn into products, I have told you this like a million times by now, there is usually energy release or energy absorption, right? Based on the energy release or absorption, you would have learned about exothermic endothermic reactions in O levels. So you know energy exchanges are there in any chemical reaction. So chemistry is not just a study of change of matter, but it is also the study of energy involved in these kind of changes. So now if you measure these energy changes that take place under constant temperature, I told you it is referred to as a enthalpy change. And if you measure the energy in each of these substances under constant pressure, we call it the enthalpy of that particular substance. But I also told you measuring enthalpy of each substance that we have over here is difficult. It is not practical in a usual lab setting, right? But we have tabulated values for enthalpy that are calculated. So if you want to calculate a enthalpy change for a given reaction, you can easily do that. Now enthalpy change, delta stands for change, enthalpy is symbolized by capital letter H. So whenever you write delta H, that is enthalpy change. So enthalpy change is equal to enthalpy of products. Enthalpy of products, if you have few products, you have to calculate all of their enthalpies, right? Based on the number of moles, the enthalpy will change. Imagine you have 2 moles of water, then you have to take 1 mole's enthalpy and multiply it by 2. 1 mole of water's enthalpy and multiply it by 2, right? Do you understand? So not just the substance you have to look at, how many of it is there is also something you have to consider, right? So enthalpy of products minus enthalpy of reactants. This will give you your enthalpy change. Is that clear? It's a simple equation that you have to come across before we move any further. So basically the energy released or energy absorbed under what? Under constant pressure conditions. When I say constant pressure, it is 1 atm pressure. 1 atm constant pressure conditions. Energy absorbed or released when a chemical reaction is taking place is referred to as an enthalpy change. Okay? Right. Actually there is more to enthalpy than this generalization, but this is what we learn at this stage. Okay, so when it comes to enthalpy, we don't have to worry too much about maintaining pressure. Why? Most of the laboratory conditions are 1 atm, that is mentioned here. Turn to page number 10 please. Right, highlight these points. These points are important. Enthalpy is a property used to quantify heat flow in constant pressure processes. Now this property is an extensive property and dependent on the quantity of substance. Underline that. Enthalpy depends on the amount of substance. Point number 5 in page number 10, bottom bit, right? Enthalpy, not point number 5, point number 4. And it says absolute enthalpy cannot be determined. Changes in the enthalpy, however, can be determined. Meaning, for us to find the enthalpy, absolute enthalpy value of R or absolute enthalpy value of products is difficult for us to measure. Like I told you, if you take this pen and burn it, there's going to be an energy change. That energy change can be measured, but the energy of the pen or the energy of the ashes, it's difficult or practically impossible for us to measure in a lab setting. Delta H for reaction is calculated using this equation. Is that clear now? Right. Now, let's take a look at how we measure these energy changes usually, easily. We say we can measure energy changes that take place. So we'll take a small chemical reaction. Now, can you remember we have system surrounding and all of that discussed some time ago? Do you remember that? Right. So now, let's take this situation. You have HCl reacting with NaOH. Right? HCl aqueous. Normally, what are the conditions, students, when it comes to aqueous? 1 atm pressure. Temperature could be, in this case, since it is not specifically mentioned, we could take it as 25. What would be the other thing that should be defined here when it comes to aqueous solutions? Concentration. What is the concentration? 1 moles per decimeter cube. So if this is a standard state of these guys, then they are having 1 moles per decimeter cube concentration. Okay, if it is standard state. Anyway, then you have NaCl aqueous along with H2O liquid, right? So of course this chemical reaction is an exothermic reaction. Can you remember that? Exothermic. Now tell me, when it comes to these exothermic chemical reactions, if I ask you how to measure the energy that is released, the answer may surprise you. We can actually do it in the lab. We can take rigiform cups. Now in this diagram, of course, they have taken 2 rigiform cups. If you want, I can draw 2 rigiform cups like so, right? So now you can see 2 rigiform cups for better insulation. Okay, and then what have we done? We have mixed, let's say 50 milliliters of this, 50 milliliters of this. I will write that, right? 50 ml. I'm not talking about standard states anymore, right? I'm just talking about simply taking these. Maybe we'll keep the concentration to 1 moles per decimeter cube. And let's say we mixed it together. Now how many milliliters do we have? 100 milliliters. Right? Imagine before mixing, there are temperatures. Imagine before mixing, their temperatures were exactly, what do you think the usual room temperature is? 25, no, we'll take 25 degrees. Both of them were 25 degrees Celsius temperature. Right? Now after we mix them together, immediately we usually cover this with a lid. We usually cover it immediately with a lid. Right? So basically I will tell you the reason for all of these steps after we explain the process. Yes, to minimize heat escaping the system. Anyway, in this lid usually there is a tiny opening for a thermometer and another tiny opening for a stirrer, right? So this stirrer, you can turn it like this, but you usually can move it up and down, so then the entire solution gets agitated and mixed, right? So initial temperature value of the two, let's say HCl and NaOH, is 25 degrees Celsius. But after mixing the two, you might notice the temperature is going up. If you have done sodium hydroxide or HCl reactions, you will see temperature goes up little by little. Let's say it went from 25 degrees to the final highest temperature it reached was 30 degrees Celsius. This is the highest temperature it reached. Now we have a temperature difference we have obtained. So based on this, students, we can calculate the overall amount of energy that got released from this reaction. Right? So let's dive into it. Okay. So first of all, let me explain to you why we use this setup. Now this setup is a closed setup.
So if the temperature increases, the energy is absorbed
Yes, energy is absorbed by what?
by the products.
I will explain that, right? So this is a problem that students have. Not only you, so many, right? That is because we haven't come to that yet. We'll come to that, right? So here, when the chemical reaction is taking place, energy is released. And that released energy, we will minimize the energy loss. How do we minimize it? By having insulation. Now this is a bit of a makeshift calorimeter. We call it a calorimeter, right? Calorimeter means anything that is able to measure the energy through a process. So calorie is a measurement for energy. We call this a calorimeter. Anyway, we have rigiform walls here. Rigiform walls are good insulators. And then we have a lid here. Again, the lid is, let's say, made out of plastic. So plastic is also a good insulator of heat. And we have not left it open, so heat will not just be leaving the system that easily. So we have tried our best with the resources we have to minimize the heat loss. Is that clear? So then, when this chemical reaction is taking place, the chemical reaction is releasing energy. Now, in this medium, students, there is HCl and NaOH. Right? As HCl reacts with NaOH, I will indicate it here. Right? Imagine you have a HCl, right, coming into contact with NaOH. Now they are present as ions. This is just a depiction, okay? Actual reaction is H plus and OH minus joined together, but I just want you to see a overall idea. So NaOH, they come together, and as they react, they turn into H2O and NaCl. Now when this reaction is happening, energy is given off. Now I ask you, to where? To what? Where did this energy that was released from this go? Now imagine this room and the air in it is where you are present, right? Currently, what is surrounding you currently? Air. Now imagine, you are here after a really long run, right? Like after running a marathon, and you come into this room, right? And I'm also in the same air that you are currently in. Would I feel warm too after a while? After a while, let's say, yes, you guys are radiating heat. Have you ever been right next to a person who has come from a run, someone who's radiating heat, right? So what happens? When he radiates heat, the air around them absorbs that energy, and air temperature goes up a little bit, right? So just like that, when these guys are reacting, the released energy goes what is immediately around them. What is immediately around these molecules? Where are they present? Just like air for you, what is present here? Water. They are present in aqueous medium, water, right? So when the chemical reaction is taking place, energy is mainly absorbed by what? The immediately right next to whatever this reactant particles, which is water. So who absorbed energy? Water did. Not the products, not the reactants. Water absorbed the energy. Is that understood? So you can see, or we can say solution, because water molecules separately, I can't just, now yes, I did say not the reactants, not the products, but just want to emphasize on the fact that water is the main one that is absorbing energy, but the more accurate description of that would be the solution absorbs energy. So when water's temperature increases, anyway the reactants and the product particles also increase in temperature. But I want you to very clearly understand who absorbs the energy most. The water right next to it. Is that clear? So that is why the temperature of this solution went up. Clear? Earlier the solutions were 25-25. That means right at the point they got mixed, the initial reaction mixture before the reaction took place was 25. But then after energy was released, water absorbed some amount of this energy and increased its temperature to 30 degrees Celsius. Now who released the energy? The chemical reaction. Who absorbs the energy? The solution or water. Is that clear now?
So is that the same which will produce by
It is
the same which will produce by the reaction?
this one. No, not this water. This is just a product, right? Now this water will also be in the mix. What I'm saying is your main attention should be going to what happens to this energy. So this energy gets absorbed by the medium. I can't say this is separated. No, it will also be water, so it will be absorbing energy. What I'm trying to say here is mainly what is happening is I just want to say if I am releasing energy right now, what is absorbing the heat? Immediate particles right next to me, which is the air particles. Just like that, if I'm a reactant undergoing a chemical reaction while releasing energy, who is going to absorb the energy that I'm releasing? Immediate particles right next to me. Is that clear? So in this case, the immediate particles happen to be the solution or the aqueous medium. Aqueous medium will increase in temperature. Is that understood? Right? So aqueous medium or solution would be a better word than just water. Right? Okay. Is it clear now? Now we have a way to measure this. And this measured amount of energy, the release amount of energy can be measured using an equation. Q equals mc delta T. Q stands for the heat or energy that is exchanged, released or absorbed, right? M stands for mass of the system, mass of this particular system without the Rigiform cup, okay? And then C stands for, yes, specific heat capacity. Specific heat capacity. All of these are given in the tute as well. I want you to note it down or highlight them. And then T stands for what? Delta T stands for what? Temperature change. Now delta T, there's another equation. Delta T. Delta T is equal to what? T final minus T initial. Right? Final temperature minus the initial temperature. Is that clear? Right. So we will calculate this value, whatever that we have here, okay? And then we'll see whether we are getting to an answer properly. I will do the T calculations here, and I will do the MC theta calculation there. So delta T is equal to T final minus T initial. T final was 30 degrees Celsius minus, here we can take Celsius or Kelvin, anything. Why? If you are talking about the temperature difference in Celsius or Kelvin is the same, right? Because I told you magnitude of 1 unit of Celsius and magnitude of 1 unit of Kelvin is identical. So the difference wise is going to be the same difference. 25 degrees Celsius. What is the value? 5 degrees Celsius. Is that clear? The answer comes in positive value. Keep that in mind, that is very important. Now, what is the mass of this substance? There's an aqueous solution here.
0.1
Right, so you are getting there. So basically, what is the density of water? We say 1000 kilograms per liter or 1000 kilograms per decimeters cube, or there's another word for that, another form of that, 1 grams per cubic centimeter, right?
0.1 kilograms.
Yes, 0.0, no, yeah, don't convert it to kilograms, right? It is nothing.
100 grams.
For what? You mean for the mass here? Right. Okay. I was just wondering what were you answering for. Okay. Yes, it is 100 grams. Now what I am trying to say here is when it comes to water, the density is this. But this is not just water. This contains two solutions, right? Sodium hydroxide plus HCl together. Now they are undergoing a reaction. Anyway, so the density slightly should change, ever so slightly, tiny amount. But we don't consider that change. What do? We consider the density of aqueous solutions to be the same as density of water. Unless and otherwise a question says so. Okay? Some question says this particular solution has a density of 1.2 grams per decimeter. Then you can't be playing around. You can say, no, we have done questions like 1 grams per decimeter cube. I'm not going to take this hint. You can't do that, right? Until they specify and give you the actual density value, you usually stick to 1 grams per decimeter cube. Is that clear? So if you take 100 milliliters means 100 cubic centimeters. What is the mass? Like you said, 100 grams. This has a mass of 100 grams. Right? So if 1 cubic centimeter is 1 gram, 100 cubic centimeters is 100 grams. Simple enough. So this is okay. What is the specific heat capacity of water? If you talk now, specific heat capacity means what? The amount of energy needed to
increase the temperature of 1 kilogram of 1 Celsius.
exactly. Yes, you can say the amount of energy that is, if you say that is required, or if you say energy needed, that means increase, right? So we can define it like the amount of energy needed to increase 1 kilogram worth of substance. This is energy, the energy needed to increase the temperature of 1 kilogram of substance by 1 degree Celsius, right? But this also can be stated, the energy needed to increase the temperature of 1 gram of substance by 1 degree Celsius. It's the same thing. Heat capacity means what? Not specific. Heat capacity means what? The energy required to increase the temperature of a given mass of substance by 1 degree Celsius. The introduction of the word specific means we are now specifying the mass. It could be 1 kg or it could be 1 gram. Clear? So for water it is 4.18. Sometimes we get the value 4.2 as well, rounded off of this. 4.18 joules per gram per Celsius, or joules per Celsius per gram, anything is fine, right? And what is the temperature change, students? 5 degrees Celsius. Do you see the relationship that we are going for? Do you see that this cancels this and per gram cancels grams? So what is the answer that you get? You have 418 multiplied by 5 joules. Am I correct? Right? Is there anything that I'm missing? No, because this 100 multiplied by 4.18 is 418 and then multiplied by 5. So 5 into 8 is 40. We have 4 and then we have 2090 joules. Since it is a large value, we can convert it into kilojoules if you like. 2.09 kilojoules. Do you understand? Right? So this came as a positive value. Why? Because the temperature change was a positive value. Temperature change could be a negative value also. Don't forget. Why? We have a formula. Imagine when the reaction was carried out, if the solution's temperature decreased, there are reactions like that. For example, if you take some little bit of glucose, I have told you this, right? If you put
This is the exothermic reaction, right?
this particular one is an exothermic reaction. Why? You can see when the chemical reaction is taking place, the energy was given off. That energy was absorbed by the solution. Solution increases temperature. So now the one who absorbed energy was the solution, one who released the energy was the reaction. So reaction is a exothermic reaction. Is that clear? Energy releasing reaction. Now what absorbed energy? So that process, that particular process was endothermic. Is that understood now? Right. So first of all, take a new heading, heat. Under heat, please take this example down. I will tell you the order of it. Don't write these arrows here. You can write consider the experiment below. So please take this first, then you can take the diagram, then take the temperature change, finally move on to this and write the calculation for the energy change. Now I was going to speak to you about a small fact. If the Q value is positive, it is always that particular process was endothermic. Now what is the endothermic process here? Increase of the temperature of water. That means water absorbed energy. Water absorbing energy is a endothermic process. But it doesn't mean this can directly be applied to this reaction. No. What we looked at was the temperature increase in water. So water absorbs energy. That process was endothermic, right? So who released energy? This guy. So that process should be exothermic. You have to work it out in your head. Do it please. Sorry? Makes sense, right? Done taking down? So we have to do a couple of questions on this. After that, we can move on to the next part. So actually students, when you take it down, we can take a small break, right? After that we'll start. We'll finish off this section. Now I need to move on to actual enthalpy changes. We'll get a few definitions in today, okay? At home, please read through this additional knowledge part. Okay, so it's a constant volume calorimeter. This is how you actually measure the calories of your food. This is the process. You might see, like, if you take a chocolate bar or whatever, it says this many calories are there, using that. Are we done? Right. Shall we take a small break then? We'll meet again at 5 and we'll go till around 6:10, 6:15, because these are all, majority of them are theory. But depending on how far we get, we'll go either till 6:15 or 6:30. Right? Actually, before we get to the definitions, we have something called thermochemical equations. We'll get to that. Okay? Right. So, yeah, take a small break. I'll see you again after the break. Right, we'll start the class. Okay, shall we now take a small note down after this? So then I'll give you one more question. Right, write down the Q value we obtained for this process is positive. Can write positive Q values indicate energy absorption, while negative Q values indicate energy released. Energy release actually. New point. The temperature.
So this is vice versa for reaction, right? This is for the medium.
This is for the water or solution, and for the reaction is the opposite, right? So that's what I was going to say. So you write right. In this particular scenario, the temperature was increased in the aqueous medium. This is a endothermic process. This is an endothermic process. You can stop there. And then write down the energy that led to the increase of aqueous medium. Energy that led to the increase of temperature in aqueous medium. Was released by the chemical reaction that took place. Was released by the chemical reaction that took place. Is that clear? Do you understand now? So therefore, the chemical reaction was an exothermic reaction. Chemical reaction was an exothermic reaction.
Small question. But the practical that we did the potassium chloride, it heats up, right? So technically, does that mean The reaction.
Potassium permanganate was in an aqueous medium? Right. What did you do? Potassium permanganate?
Like we mixed it with something and it like heat up.
You mixed it with, what was the color change that you observed?
First green.
Green. So it heated up. Right. So basically,
Technically, in that case, the solution was endothermic, right? But because it was
yes, so the heat absorption in the aqueous medium is an endothermic process. But whatever the chemical reaction that took place was an exothermic process.
so that's why since it absorbed heat, the vessel was hot.
Yes, the medium absorbed heat, so the medium became hotter. Right? So I think, do you remember what it was that we have KMnO4 reacted with sodium hydroxide?
Yeah, sodium.
Sodium hydroxide, they form potassium manganate. Potassium manganate 7. Right? So, I'm sorry students, give me a second. Sorry about that. Right, so now when it comes to any chemical reaction, this is the situation. So one of the interesting things is when you are talking about an exothermic reaction, you feel the heat that is released. So you can, you know, when you break it down into the chemical reaction and the medium, then we talk about this medium absorbing energy is endothermic, reaction is exothermic. But all that aside, when a chemical reaction is happening, when you feel the medium heating up, that means what? Something is releasing energy. Right? Simple as that. Right? What is releasing energy? The reaction. Right? So because of that, reaction releases energy, temperature increases. It is a exothermic reaction. Or if it is a endothermic reaction, as the chemical reaction takes place, heat will be absorbed. So when you touch the system, you will feel the system is cold. Why? Because when the chemical reaction is happening, reactant molecules absorb energy from the immediate particles around it. Immediate particles happens to be the medium particles, whatever water or aqueous medium particles. So they absorb energy from that. So the medium cools down. So why did the medium cool down? Because some amount of the medium's energy was taken in by something. Who took it in? The reaction. Is that clear now? Write down another question. Write down another question. When sodium carbonate was reacted with sodium carbonate, Na2CO3 was reacted with ethanoic acid. Ethanoic acid is this. If you can't remember, ethanoic acid. When sodium carbonate is reacted with ethanoic acid, the following were observed. Write down these details. You can take this down and write total volume of mixture, total volume of solution actually. Temperature, let's say, went from 25 degrees Celsius to 17 degrees Celsius. It went down. And then you can write, if you want, you can write initial temperature 25 degrees Celsius, temperature final is 17 degrees Celsius, and the reaction mixture contains two things. One is sodium carbonate, Na2CO3, and the other is ethanoic acid, CH3COOH, and it turns into CH3COO Na plus water, so and carbon dioxide actually, CO2. So basically two of them will be needed, two of them will be produced. Each of them will give H pluses to carbonate ion and turn into carbonic. Carbonic breaks down immediately, form water and carbon dioxide. Right? So everything should be balanced at this point. Yes, everything is balanced. Now I want you to find out in the question, right? Find out the energy absorbed or released. Find out the energy absorbed or released. That is part A. Part B, based on that, comment on whether the reaction is exothermic or endothermic. No need to explain the whole medium absorbed energy or medium released energy, whatever. It doesn't have to be explained there. You just have to, based on the information you get, explain whether the reaction was exothermic or endothermic. Do that one. Right, I'm sorry, you couldn't hear me, right? So yeah, as I was saying, this was a endothermic process. When it comes to the chemical reaction, this negative sign is there because water was releasing energy into what? The chemical reaction. So I was explaining there is a chemical reaction happening in the medium. Chemical reaction was absorbing energy, right? So the water had to release some of its energy to the chemical reaction. Water is releasing energy. So what is that? When I'm releasing energy, that's the exothermic process. So what water did was exothermic process. What the chemical reaction did was an endothermic process. So this guy was absorbing energy. From where? From the medium. So the aqueous medium was releasing energy. This guy was absorbing. So this is a endothermic process. What water did was a exothermic process. That's why when we use Q equals mc delta T, the sign was negative. The sign was negative because we applied Q equals mc delta T to the medium. So the medium was releasing energy towards the chemical equation. Is that understood?
Yes.
Right. Take a new heading, thermochemical equations. Thermochemical equations.
So what is the now?
Thermochemical equations. Write down under that a balanced chemical equation. A balanced chemical equation together with standard conventions adopted, and including the value of delta H, within brackets write O delta H naught is referred to as a thermochemical equation. So this is a good example. Now this is a usual equation, normal equation of solid water turning into liquid water, ice melting. If I give you delta H value, which is 6.02 kilojoules, I will write it here, I wouldn't have enough space otherwise. Delta H equals 6.02 kilojoules per mole. That is a thermochemical equation. You have the basic equation with the states and all that, followed by the enthalpy value for that reaction. The unit of enthalpy is kilojoules per mole. That's the unit of enthalpy anyway. Now over here, when you use that unit, kilojoules per mole, for a given reaction like this, I have a question for you. if, now tell me what this means. Now genuinely, like when you see this, something like this, you have an idea about it, right? Tell me, what does this delta H equals 6.02 kilojoules per mole means?
The energy change that has taken place when change in states.
Energy change that takes place when this happens. This is a positive value, right? So what does that mean? This is an endothermic reaction or exothermic reaction? Now this enthalpy value is directly for the chemical reaction, not for the medium or anything like that. So directly for the chemical reaction, if it is a plus value, what is it? Positive enthalpy changes or positive Q values are always energy absorbing, meaning what? Endothermic. Whenever
It's the Q value, right?
Absorbs energy.
Enthalpy is the Q value.
enthalpy is H, Q is the energy, right? H is enthalpy.
It would make sense because ice turns to liquid.
Yes.
Yes, anyway ice needs to absorb energy, right? So if the value over here is positive, that means it is endothermic, right? Don't get it mixed up. Endothermic reactions are always positive. So now
Sir, that value 6.02 is Q value, right, sir? Energy value?
no, it is the enthalpy value, delta H.
Delta H.
So you can call it a Q value, but if you have measured that Q value at a constant pressure, you can call it enthalpy. Do you understand?
Yes.
So now sometimes you can, let's say, imagine you go and ask someone to kneel down, right? Is there something wrong or right? Wrong, you have no right to do that. But imagine you are a disciplinarian, maybe in 1995, right? Now you can't do that. So at that point, imagine you are a disciplinarian and one student is like, disturbing the entire class. So the disciplinarian comes and says, kneel down. Is that now okay? Yeah, from that standpoint, at that point, would have been okay, right? Do you understand? But the action is the same. So to make your point, when it comes to energies that we measure, we use these Q values to measure energy. But if that energy is measured under standard, not standard, under the constant pressure conditions, using 1 mole of substance,
That Q value is for the medium. So that value, if that value is positive, the reaction is endothermic. Negative.
no. When forget about everything. Whenever Q value or H value, now if you want, you can write it down somewhere, right, before we move any further.
If Q value
Q is energy.
yes, if it is positive, the chemical enthalpy change of the chemical reaction, not the enthalpy change, energy change of the reaction is endothermic. If it is positive, and if it is negative, that is the energy change is positive.
Can I explain? Right? So listen up. Don't think about the medium and the reaction separately from now on. Right? Just remember this fundamental rule. There are always energy exchanges taking place. Imagine monetary exchanges. If I give money, someone has to receive it. If I'm a chemical reaction, if I'm giving away heat, someone has to receive it. Right? If energy is received, it's an endothermic process. Forget about the reaction word. Use the word process. If energy is received by something, that something underwent endothermic process. Energy received. If I give off energy, I am releasing energy, or if I am giving off energy, I am undergoing a exothermic process. Is that clear?
Yes.
So if energy is released, the Q value for that, imagine I am undergoing exothermic process. So from my standpoint, always the enthalpy or the Q, you can calculate Q or enthalpy for any energy related processes. So if I am undergoing an exothermic process, the sign is negative. Exothermic means always, always negative, right? And if you see a Q value or a H value that is positive, that meant that thing underwent a endothermic process. Now, for your understanding, if you have a reaction happening here, right? If the reaction is releasing energy, what is happening to the reaction? Reaction is undergoing what? Exothermic reaction. So if you calculate its enthalpy, delta H, what kind of value would it be? Positive value or negative value? Enthalpy will be negative. Why? Energy was released. So this released energy was absorbed by whom? The medium. For the medium, what happened? Medium all of a sudden got energy, right? Imagine I started feeling like throwing away money. What happens? I am becoming poorer, you guys will becoming a bit richer than we are currently at, right? So why? You are gaining something, I am losing something. So now the reaction is losing energy, medium is gaining energy. So this delta H value is going to be what then? Positive, right? Endothermic process always is denoted by a positive delta H value or positive delta Q value. Not delta Q, positive Q value. Is that understood now? Right? So the opposite of this argument is also true. Sometimes when a chemical reaction is taking place, the reaction might be absorbing energy. Right? Reaction might pull energy from the medium. Right? Reaction is absorbing energy. Then what happens? The medium is losing energy because reaction is absorbing energy. So for the medium, the delta H value will be what? Medium is losing energy, it's minus. Reaction is absorbing energy, it will be plus. Delta H would be plus. Is that clear now?
Yes.
Yeah? So, doesn't matter whether it's the reaction or the medium, the convention is always the same. If the Q value or delta H value is negative, that denotes a exothermic process. If the Q value or the delta H value is a positive value, that denotes a endothermic process. Now for this given process, this given entire reaction, this delta H is given for this chemical reaction, right? Not for the medium or anything like that. So what is the value here? A positive value. So this process is an endothermic reaction or an exothermic reaction? Endothermic for sure. Right? Do you understand? Now, some of you have done these parts in school. So now I want to ask you this question. What does this per mole mean? Those of you who have done it. Per mole, I'm asking, yeah, it's a unit, right? What does per mole mean? Is it for single 1 mole of this turning into this? Or energy released?
Energy released by 1 mole of
1 mole of water when turning it into liquid water. Okay. Then I will write another equation. Can you remember the definition of thermochemical equation? The reaction written along with the proper states and along with the delta H value. Now for this reaction, the delta H value is 12.04 kilojoules per mole. My goodness, what does that mean? Now earlier you argued when 1 mole of this turns into this, that's what per mole mean. But now there are 2 moles of water turning into 2 moles of liquid water, solid water turning into liquid water, but the unit is still per mole. Should it be per 2 moles? Right? Isn't it? We are taking 2 moles now. So then at that point I am asking you, shouldn't it be a bit wrong to write per mole if we were only talking about 1 mole of this? Now, to your surprise, if this was even 10 H2O, then it will be a multiple of this with per mole as the unit, not per 10 moles. What is happening here? Now, this is where a lot of students do lack a bit of understanding, sometimes even some teachers do. So, this reaction, yeah, listen up for the time being. So what happens is, what we do is, this value is given, or I'll interpret what this means. 6.02 kilojoules of energy is released, since it is not released, as it is absorbed because it's a positive charge value. 6.02 kilojoules of energy is absorbed when this particular chemical reaction takes place this many times. Do you understand? This entire chemical reaction has to happen a 1 mole amount of times. At that point only this much of energy is given off. Do you understand? It is the 1 mole concept is not applied for one of this or one of this. It is applied for the entire process, right? For it to happen 1 mole many times, when it happens 1 mole many times, this is the energy change. Is that clear? So whenever you see the word per mole, that refers to the chemical reaction written as is. Now this chemical reaction is written with a 2 as the coefficient. So when this chemical reaction happens as it is written, 1 mole many times, the energy absorbed is this much.
So without that, it is small, very small.
Yes, if it is happening just a single, like 2 water molecules with forming 2 liquid water molecules, extremely small energy value is going to be exchanged. But if you see this happening like 1 mole many times, right? So to make it happen 1 mole many times, you have to take 2 moles of this and turn it into 2 moles of this. Simple, right? If you want to see this happening 1 mole amount of times, so you have to take 2 mole, 2 mole, right? So if you understand that, that is one of the most important points, because sometimes students don't understand what per mole means, just randomly writes it down. So please write a small this thing, write down. Write the first equation, don't write the other parts, please write just the equation. H2O solid turns into H2O liquid, write it down along with the enthalpy value, right? H2O solid turn into H2O liquid along with the enthalpy value, and then write right? Did you write this and this part? That's the thermochemical equation, right? Otherwise it's just a balanced chemical equation, right? Then write the per mole, right? Hyphenate the per mole part. The per mole in the unit for delta H, means that this is the enthalpy change per mole of the reaction or process. Per mole of the reaction or process, it is not finished yet. Enthalpy change per mole of the reaction or process as it is written. As it is written, right? Then write this one, second one, along with this, write down, along with this. can write, as mentioned above, the per mole in the unit of delta H indicates the energy change that takes place when the above reaction written happens 1 mole many times. Above reaction written happens 1 mole many times. Is that understood now? The per mole is for how many times the reaction is happening, not for individual reactants. Okay? Then we have to finish taking this tiny note down. Right. First one, as a small paragraph, start writing. It is essential to specify a balanced chemical equation when mentioning the enthalpy change of a reaction. Enthalpy change of a reaction. Now, why do we say that?
Because we don't know as
Yeah, because
one reaction we have.
exactly, when you write this one, imagine you just thought just water turning into solid water turning into liquid water, and just you thought you're going to be writing it like this. Then this is wrong, because these two can't be the same, no? You have to be very specific. It has to be a nice balanced chemical equation with actual coefficients, and for each written balanced chemical equation, the enthalpy change would be different. So here, for example, for this, the enthalpy change is that. But if I write it like 3H2O, right, solid, turning into 3 water liquid. Now you can figure out what the enthalpy change is. What is the enthalpy change?
18.06.
Yes, 18.06 kJ per mole. That means when this happens 1 mole many times, this much of energy is absorbed. Is that clear? Do you understand now?
Yes.
Okay. So then write guidelines for writing thermochemical equations. Guidelines for writing thermochemical equations. Right, first one. When writing thermochemical equations, always specify the physical states of all reactants and products. Physical states of all reactants and products, because they help determine the actual enthalpy changes. We'll take down a small example. They help determine the actual enthalpy changes of the reaction. write down reactions numbered, okay? Reaction number 1. So we are writing methane combustion reaction. Methane gas reacts with O2 gas. Sorry? Some 800 value, 890.4. Right. So this turns into carbon dioxide gas. And what is the standard state of water? H2O liquid. Now since I have taken a lot of space, I can't write delta H directly here, which is not ideal. No, then that can't see. Bear with me just a second, students. Sorry. I will start here. We have reaction number, reaction 1. We have CH4 gas reacting with O2 gas, turning into CO2 gas and H2O liquid. Now we have 4 hydrogen, so we have to have 2 water molecules here. So then at that point we have 2 oxygens and 2 oxygens altogether, 4 oxygens. To get 4 oxygens you have to write 2 here. Is this balanced? Yes. So the delta H value here is 890.2 kilojoules per mole. That means when this reaction happens 1 mole many times, 804, so 890 kilojoules of energy is absorbed. Actually, minus, released. Right? Burning of methane is exothermic. Right? Then reaction 2. The same reaction. I will make a small difference here. I am changing the state of one of the products. H2O gas. What do you think happens to the enthalpy? Will it increase or decrease? So I will write the enthalpy value without keeping you in suspense. So delta H is equal to minus 102.2 kilojoules per mole. Let me double check these values. I have it here with me. It is, yes, 102.4. Actually these values are 4s. I'm sorry, this is 4 and this is also 4. Is that clear? Now tell me, now the first guideline was when you are writing electrochemical equations, specify the states. Why is that important? Because based on the state of the products and the reactants, the enthalpy value that we get to is different. Now can someone explain to me why this magnitude was different here?
Because some was released but some was reabsorbed, change the physical state.
Exactly, very good. So here the energy is released when this reaction is taking place, right? This much of energy. Usually at room temperature pressure conditions, water is in a liquid state. But imagine if you want to convert this water also to a gas by the reaction. Now it's happening actually when it comes to high temperatures generated here, some amount of water could turn into this. So tell me, how much, then what happens? Certain amount of energy will be absorbed for that process as well. So out of the total amount of energy released, some amount will be reabsorbed for this. I immediately, actually today in the beginning of the class, this is something that I discussed. Can you remember? So here same amount of energy is released in both cases, but in this case water is turned, liquid water was turned into gaseous water. So some amount of energy was again absorbed. So what we see as the enthalpy change is the net energy absorption and net energy release, right? So what is this? Is it a net absorption or net release? Net release. What is the net release value? Smaller than the value that was released earlier. Is that understood now? Yes? Okay. And then please write the third reaction. Then after that, did you copy this first two down? Third reaction is this 2H2O liquid turning into 2H2O gas. Can someone tell me this is something you can calculate and tell me. Can you tell me the delta H value here for this process? You should be able to tell me by looking at this above two reactions. This is two water molecules that were present here turning into two gaseous water molecules. How much of energy was absorbed? 88.0 kilojoules per mole. Is that clear? Do you understand? Please write down a small sentence.
Still writing.
Okay, quickly write it down. No need to show these arrows, okay? The arrows were there for your reference. When you're writing it down, don't write the arrows like this. Energy indications are not needed. Done? Write down.
Mix.
I will give you some time to copy it down, right? For the time being, please note this down. I will not erase this now itself. So write down the enthalpy change for the reaction 2. Enthalpy change for the reaction 2 is minus 802.4 kilojoules per mole rather than minus 890.4. Can write. This is because in reaction 2, state of the water produced is gas or is gaseous, right, compared to liquid in reaction 1. You can write 88 kilojoules are needed to convert 2 moles of liquid water to water vapor. You can write this indicates the importance of specifying physical states. This indicates the importance of specifying physical states. Okay? Right. If you want, you can finish down. Right. Right?
On the angle, even if you're sitting down,
Sorry?
if you're sitting down, I must take.
When I was sitting down.
It's a capturing.
You want to capture me? Okay, no problem there. Right. So, while you take down this thing, I will explain something. Now, what about? Can you remember? Look at after touching this thing. Anyway, when I have to go wash now. When it comes to the very first solid water turning into liquid water part, can you remember 6.02 kilojoules per mole example I did? Can you remember when we took 2 moles of solid water turning into liquid water, what did we do to enthalpy change? We multiplied by 2. So you understand that part, right? But we have to take it down as a guideline for writing thermochemical equations. Yes, right. So take a second point. So the first guideline was number 1, the first thing that you wrote, number it number 1, and then write number 2. If we multiply number 2, if we multiply both sides of a thermochemical equation by a factor of n, if we multiply both sides of a thermochemical equation by a factor n, then delta H must also change by the same factor. Then delta H must also change by the same factor. Right. So we'll take this simple example first. Let's say I wrote it earlier as well. What was the delta H value, students? Quickly tell me. Delta H is equal to 6.0 kilojoules per mole, right? This is a value that I gave you, rough approximated value. So this is an energy absorbing process because enthalpy value is positive. Now imagine I rewrote this same equation by tell me a factor. Don't tell me 2. Tell me a factor. Don't tell me a big factor also. Okay, we'll take 6. Right. So let's say we write this as 6H2O solid, and here also we have multiplied this side also 6H2O liquid. So then what happens to delta H, students? Delta H value, which is this value,
37.2.
this value also gets multiplied by 6 kilojoules per mole. So what is the answer then? 36.0 actually 36.12 kilojoules per mole. Is it understood? Yes? Write it down. That's the example. Write it down. Are we done? Brilliant. So the last point that I would want you to learn is this. Now this was the second point, right? Right, the third point. When we reverse an equation, the magnitude of the delta H, for the equation remains the same. Yes, right, remains the same, but its sign changes. As a new point you can write, if a chemical reaction, okay, right, if a chemical reaction under the same point but as a new line, right, if a chemical reaction absorbs energy when the reaction is reversed, the same amount of energy should be released. Yes, exactly. You can write down example. Now you can see we turn solid water, ice, into liquid, right? But we can easily do it the other way around as well. If you take liquid water and put it in the fridge, right, what do? What do you get? H2O solid. So what have we done here? We have removed energy. How much? The same amount. But now it has a opposite charge or opposite sign, right? Earlier energy was absorbed to melt water, so you have ice. To melt ice you absorb energy, right? Turn into liquid water. If you take liquid water, if you remove energy from the liquid water only, it will turn into ice, right? Because solid state and liquid state, there's always energy gap, right? So the energy gap is always the same. You understand? Is that clear? So if you take this water, now usually we specify temperature, imagine 0 degrees Celsius, so we can turn solid water to liquid water at that point, and then the energy absorbed is that much. If liquid water turns into solid water at 0 degrees Celsius, the opposite of that energy or relationship can be found. That means you have to release that much of energy to get to this point. Is that clear? Do you understand? So we can demonstrate this in energy profile diagrams, right? Now imagine this is where you have your liquid water, H2O liquid. This is where you have H2O solid. So imagine you have solid water turning into liquid, then it is a energy absorption. We always draw the arrow from the reactant to products. We are talking about the first one. For the first one, reactant is what? Solid water. Product is this. So let's say X amount of energy was absorbed, right? So this is a positive value. Arrows pointing up always indicate positive values. Now let's consider the second reaction. Liquid water turning into solid water. So we are starting from liquid water, coming back into solid water. Has the gap changed? No. but the arrow is downwards pointing now. So it is minus x. Is that understood? Right? So simple enough, right? So those are the main points, students, that I wanted to leave with you. And then after that we move on to the next part, which is enthalpy changes, and I want you to be familiar with different types of enthalpy changes. So I will give you a small brief introduction to that, and then we'll stop the class there. So there's something called standard enthalpy changes. Standard enthalpy changes. If you
So should we take that down?
If you want, this example, right? Take it down.
No, the energy profile diagram.
Yes. We can call it an enthalpy profile diagram as well, if you write enthalpy value here. Take it down. Now for the exothermic endothermic part, I was in a bit of a rush to get to this point. I didn't give you that note there, but I'm pretty sure you know what exothermic endothermic means, right, from O levels onwards. But if you have a problem with that, let me know. I will give you that note. And today also we discuss what exothermic endothermic processes are. You have a question?
Our school, they said when we write chromium, that Hans rule that if the 4 is 2 and 3d4, right?
Mm-hmm.
Then the one of this goes to D and it stabilizes it. Then they say we need to write 3D first. Then the
Who says?
our school teacher.
It's like this. There's no such need. Both are correct. I can show you multiple books that denote that. Even in our syllabus, it is the case, right? But we prefer writing it that way. We prefer writing 3D and then 4S. But writing 4S and 3D is absolutely okay, if you have any doubts. The only reason why we actually prefer writing 3Ds and then 4Ss, after writing it the correct way, we sometimes switch and we write 3P, 3D5, 4S1, right? The reason why we do that is when we are removing electrons from it, we start from 4S. So the students doesn't get confused if you have already gotten into your head, we are writing it this way only, right? Then you know, then we are removing electrons from this end, starting forward. Is that clear? So that could be the only reason why she is saying that, right? Okay, so when it comes to enthalpy changes, students, basically enthalpy changes are very specific. They specify everything. For example, if you're talking about enthalpy change of formation, as I mentioned earlier, they specify everything that you have to know about that particular reaction, right? Let's say we'll take something like enthalpy change of combustion. Enthalpy change of combustion very specifically refers to carbon solid, not just anything, carbon solid graphite, which is the most common form of carbon, right? This is the standard state of carbon. Now carbon is present in nature in few different ways. We have coal, we have graphite, we have diamonds, right? Those are called allotropes of carbon. But most abundant is graphite. So we say carbon solid graphite is the most abundant form. So if you are talking about combustion enthalpy, we can write it like this. Carbon, 1 mole of carbon is combusted in the presence of enough oxygen to form whatever the product. So our main focus is what? When it comes to combustion enthalpy, taking 1 mole of the thing that we are trying to burn, right? And others also should be in their standard states. Is that clear? So there are so many different types of enthalpy changes. Some names would be enthalpy change of combustion, enthalpy change of formation, enthalpy change of neutralization, atomization, right? Lattice enthalpy, ionization enthalpy. Ionization enthalpy. We learned about ionization, didn't we? We did. First ionization enthalpy. Now, at that point, I gave you a definition. Can you tell me what the definition is?
The
Amount of energy required to remove
one electron from
One-
1 mole of gaseous.
1 mole of electrons from 1 mole of gaseous atoms.
To form?
to form
From
1 plus 1 charge.
Very good. So you all remember. I'm happy about that, right? So the amount of energy or energy change, right? We always refer to the word energy change or enthalpy change that takes place when 1 mole of gaseous atoms lose 1 mole of electrons to form 1 mole of plus 1 charged ions is referred to as the first ionization enthalpy of a given element. Is that clear? So just like that, do you see there is a very nice outlined, defined enthalpy, different types of enthalpies that are out there, and then for those we have calculated the enthalpy changes. Now there is a reason for us to do this, so that whenever you come across a chemical reaction with a little bit of an unknown enthalpy change, imagine you have written a chemical equation, you want to figure out the enthalpy change of that. So you can find the enthalpy change with the use of the other enthalpy changes. Right? We are going to be learning about that next week. So first of all, we need to learn all the different types of enthalpy changes. So the first hour also will be dedicated to that. Then we move on to Hess's cycle. Right? That is the most important part of the first part of the enthalpy related lesson. And then we have something called Born-Haber cycle, the next most important one. Right? So, but to get those two right, you need the enthalpy or what is defined as the standard enthalpy change idea very clearly in your head. So, standard enthalpy change is usually denoted by delta H note. This note is there only to say, okay, this is a standard enthalpy change, meaning the states of each reactant and products are defined, so we know the conditions in which it happens. It's not some randomly. Now for example, when you say now SLS standard, quality standards are there, right? That means, do you feel like a bit worried to buy something like that with a proper quality standard, quality seal? No. But let's say you go to Goal Face, right? You eat a isovadi, right? What happens the next day? Right? You can't get up from the toilet. Why? I'm not saying all soda is like that. I'm just trying to say you might have experienced that. So that is why might not be having the correct standards. They might have some food products that are there from 2-3 days ago that are refried again and given to you, right? But when it comes to certain other products that are out there in the market, they have quality standards. Now just like that, here also we are following standards. We know the conditions of each of these reactants and products, so we can be very sure of the energy output or energy absorbed, right? So since we know these, we are very sure about the communicated energy value. Is that understood? So if you have followed all of those standards and found out an enthalpy change, those types of enthalpy changes are referred to as standard enthalpy change. Delta stands for change, H stands for enthalpy, this stands for standard. And apart from that, you will have different lettering here. For example, ionization, you can have I, or F would be what? Formation. If you have C, combustion. If you have ATM, atomization. If you have NEU, neutralization. So on and so forth. Is that clear? So for each of these definitions, there are very clear outlines. One is the conditions. They say the element should be in standard state and it should be having standard state conditions. And then apart from that, they also mention that we are looking at 1 mole of reactant turning into this, or some definitions say we are looking into only producing 1 mole of product. Is that understood? So it's either going to revolve around reacting 1 mole of reactants or producing 1 mole of products. Is that clear? So I will talk about these definitions later on, because without the definitions you can't do enthalpy calculations. If you don't know definitions, you can't do enthalpy calculations. Simple as that. You have to have a very good understanding. Okay? For example, if you didn't know first ionization energy uses gaseous atoms, you could normally write it without writing gaseous state. That means, let's say for example sodium. If you wrote sodium's ionization enthalpy as Na solid turning into Na1 plus electron, that is absolutely wrong. And if you calculate an enthalpy change for that, you are absolutely wrong, because then we have to take sodium solid turning into gaseous part as well and then removing an electron. Do you understand? So then the equation that you have written has an additional energy amount in it, which is wrong. Is that clear? Right. So hopefully you are clear about what awaits you next. So we'll move on to that next week. Next week onwards, we are going to only look at calculations. Right? Okay. So come prepared for that. At the back of the book, there are many questions. At home, feel free to try them. If you have studied them, if you have done questions in school, you can attempt these questions as well at home. Okay? If you haven't done it, don't touch it. Right? I will teach you how to do it. All right. I will see you again then next week. See you all. Bye. Good night.